My name is Wang. I joined Encina in 2018. We are a Houston-based company. So at Encina, we are trying to develop a practical process which lead a transition to circular economy. So more specifically, those are the major steps in this process. So at the first step, we'll receive the waste plastics from the recycling facility. We'll then combine the conventional mechanical recycling technology with the new advanced recycling technology to prepare the material which meet the reactor specification so that we can transfer the material into the reactor and make the reaction happens. So in the reactor section, as we have the prepared material feed into the reactor, is through a catalytic conversion. The plastic will be converted to the desired chemical products. By tuning the, catalyst formulation, the operation condition, process condition, we are able to selectively extract chemical molecules from the chemistry. So the reactor effluent will be then, sent to the distillation towers. The separation process is similar to the conventional separation technology. So the desired material will be extracted from the mixer stream, and the chemical product will be prepared for the commodity market. So here I'm showing you the scale-up process that we are actively working on right now. So we start with the small scale, the bench scale unit. We do a lot of tests, like screening the catalyst in the fixed bed. We also have run some small scale fluidized bed where we are able to measure, to build the fluidization curves. And we use those hydrodynamic information to calibrate the CFD model. So we do have a slightly larger kind of pallet unit fluidized bed, and it's a hot unit. So we are able to collect a lot temperature-related information, and that's a good information for us to do the validation of kinetics, which we use in the CPFD model. So currently, we are working on the demo unit and demonstration unit and the large scale cold flow unit. So for the demo unit, we are able to establish a full catalyst circulation loop. And also, in this demonstration unit, we have a whole complete process. So from the front end, where we prepare the material, the plastics, and in the middle section, reactor, we're able to demonstrate the chemical conversions. And then the in the downstream, we demonstrate how we separate the chemical products from the reactions. From the simulation-wise, we're trying to study something we cannot easily detect it from the experiment test. For example, we're trying to study now how the feed material dispersed in the vessel, which is very important for the for control the chemical reactions. Of course, we also get the temperature profile, the hydrodynamic data, which could use for calibrate the model. Also trying to build engineering correlations. For the large-scale cold flow test, so we have two objectives. So the first thing is really to study how the Encina IP design could affect on the hydrodynamic performance. And also we're trying to better understanding like a new concept, like in terms of the separation technology. So with the help of CFD, we are able to look those, for example, how the particle-particle, gas-particle interacting, and how they are, how those physics being affected by the Encina IP design. We are able to look at those phenomena closely with the help of the CFD. So the last stop is the commercialization. So I think from the CFD perspective, everything we have done in those smaller scale is really kind of like a learning experience, how to calibrate the model, how to develop the kinetic package so that we can build a strong case in a commercial scale unit simulation. I think the objective or the main goal of doing a large scale simulation is really trying to optimize the design and detecting any potential problems before we commit to the commercialization. So, yeah, the first thing I want to show is really how the model calibration looks like. So this is a 6-inch small scale fluidized bed. We have so the particle initial loaded, and then the gas is fed from the bottom. So the gas flow was controlled starting from like almost 0, and then we slowly increase the gas flow to a certain point, and then the velocity will start to decreasing back to the beginning velocity. So the pressure drop was measured at different elevation. So we convert the pressure drop to bed density. So you can see here on the top plot, which is the velocity increasing curve. So you can see the second calibration curve is really matching the experimental result surprisingly well. We catch the transition point very, very well. So same kind of story for the velocity decreasing curve. You know, so the bed density was matched by the second calibration curve, and also the transition was predicting nicely. So those experiment was done in a relatively low velocity regime. So we also interested some other, velocity range, like the higher velocity range. So we have done this 80-inch fluidized bed. So with this one, again, we have the background gas from the bottom, and then it starts fluidize the bed at higher velocity. Some particle will collect it in the deep leg of the cyclone and return back to the main columns. So in the CFD, I didn't model this cyclone part. Instead, I'm using this BC connection feature in the CPFD. So any particle come out from the pressure BC will return back to the fluidized bed in the bottom. So I use this injection BC feature to model the the background gas. So yeah, if we look at the result, so this again, this we have done 3 different calibration with the same adjusting as the previous work. So we can see all the 3 calibrations seems kind of matching the experimental result. However, I have really got some difficulty in order to match the higher velocity, like those ultra high velocity range. But still, when we measure the difference between the experimental result and the modeling, so the error is like within 10%. And for the majority part of this curve, especially in the middle part, it follows the experimental result pretty well. And so we are pretty satisfied about the drag model calibration. So we kind of select the calibration curve 2 to proceed other simulation work. So, as most of us, we like to do simulation with a very fast speed. So this is a commercial scale unit. So initially I was thinking this probably take months to get some simulation result. So I conduct 2 set of experiment with different grading resolution. The lower resolution was about 150,000 cells, and the high resolution is about 600. So the computation time did show a huge difference. With the low resolution, we are able to get 100 seconds within a full day. And with the high resolution case, we'll need 5 days in order to get the same amount of computational time. So we did go ahead to check the result consistency, and we checked the superficial velocity and bed density. And in general, I think the 2 set of results are agree with each other very well. So only one minor thing here for the bed density. So at one elevation, we do see a gap, a consistent gap between the low and high resolution, but that gap is really within 3%. So compared to the overall bed density, that's a very small number. Another interesting task, like checking, is we look at the mass fraction of the effluent gas. So as you can see here, I'm showing you the bottom portion of this reactor. We have those cutting slices. I'm showing you here an example in the force flux plan. So we are trying to getting the concentration along this x direction. So here I have 10 data points. So I plot those concentration into this graph here. So you can see, for example, the top plot here at 30 seconds, we tracking the gas concentration for both experiment, and you can see the result is not exactly the same from different experiment, but that's also not I'm really looking for like a exactly match. I'm more look at the trend. So here I think in the beginning, like in the beginning part, we are seeing a high concentration profile, and that's reflected by both experiment. And then in the middle part, it shows some fluctuation, but they all kind of like in a similar range. So in the end here, you can see they are decay to a very low concentration. So I think in general, these two, even though it's two big different in terms of resolution, but they are reflecting the same kind of story. So with those data checking, we have decided, let's try the low resolution with the rest of the test, because it's really provide a big time advantages. So here I'm showing you the first kind of simulation result from this commercial application. So now I'm showing you the top panel here. This is the top view of the reactor. The first one is no Encina IP, so it's almost like an empty vessel. And the third is the configuration with the Encina IP. So in the center here, we do have a geometry. That's why you see an opening over there. So the bottom panel here, again, is showing you the particle volume fraction, but you look at it from the side, and this is only a thin slice. So probably, I don't know, 100% of the total reactor, 1% of the total reactor thickness. So now, let me show you. So now you can see, without the Encina IP, everything, all the gas is really just flowing in the center. So you really can see like a big particle splash in your free bar, and all the gas is accumulating in the center. So you will get really, really poor gas and solid mixing, and even solid mixing. You can see like, all the solid is like really dense bed and seems like a stagnant area along the wall. So that's really poor solid mixing as well. But if we look at those improved design, so you can see clearly, first of all, we saw the particle volume fraction is more homogeneous. So we don't see like a clearly dead zone or clearly, gas, like gas in the center, like a channel, which we saw in this case. Instead, we are seeing a more well-distributed fluidized bed. So to look at this thing like from a different perspective, so now I'm showing you like a whole view of this reactor in terms of height, but really I'm cutting, this is only showing 25% of the diameter, in the direction perpendicular to the screen. So here I'm showing you a tracer analysis. So you can see we have fit the tracer from at 50 seconds, and it's very short duration. So now I can show you without this, the Encina IP design. So you can see all the particle is initially just blowing up to the top level, because we have a very strong, gas stream in the center. However, with those, configuration 1 and 2, you can see the particle is more spread and is better mixed with the spent catalyst. But we do detect some problems. If you look at the lower portion of this, this catalyst bed, so we are seeing in one, on the left-hand side, we are seeing more cold particles. and on the right-hand side, we are seeing more hot particles. So it's clearly temperature maldistribution, and more importantly, I think the maldistribution is one thing. Another thing is really we don't like those cold temperature, because that will be really affect the chemistry. So we're trying to eliminate those cold temperature, and we are trying to look at something like quantitatively. So we're trying to look at the particle mixiness. So I'm showing you like 10 different elevations. So we are trying to measure the particle concentration at different elevation. So here in this plot, I'm showing you the tracer mixing over ideal mixing. So the tracer mixing is really just the particle weight tracer weight percent at selected elevation. So the ideal mixing is we are assuming the tracer particle was evenly distributed across the entire fluidized bed reactor. So you can see at the beginning, we feed the tracer at 50 seconds. At the beginning, we see a big variation, which is expected because all the tracer just accumulate around the nozzle. It's not being well distributed yet. But now you can see as time goes, it takes about 20 seconds for the tracer is fully mixed with the spent catalyst and well distributed across the entire, entire fluidized bed, from the bottom to the top. So we are seeing a very good, mixiness, particle mixiness. And after this 70 seconds, it still shows some kind of consistent result. So if you look at this, mixiness, like I showed in the tracer video, right? So we do saw that big temperature variation in the bottom section. So now I'm showing you this plot. This is the tracer temperature as a function of elevation. So we're trying to look at the temperature, the tracer temperature at different elevation of the reactor. So the variation is really, so the standard deviation here really showing you at one elevation, what's the temperature difference in the radial direction. So first of all, you can see that in those higher elevation, we seems to have a very good temperature consistency. So at different elevation, we have the same temperature, and also at all those different elevation, we have a very small standard deviations. That means on the left-hand side of the reactor to the right-hand side of the reactor, we get a similar temperature. So that shows a very good, mixing, particle mixiness in both radial and axial direction. However, the problem is really in this lower elevation. So we do saw those large variations, which means one side of the reactor is cold, another side of the reactor is hot. So we're especially trying to remove those low temperatures. So how we solve this problem? So first of all, we have two kind of options. One is from the design perspective, another is trying to improve the operation condition. So now here I'm showing you. So from this, you can see this is the original design, and that's exactly what we saw from the tracer analysis. We have one side of the vessel is really cold. So you have to see this really low temperature, and on another side, we see a very high temperature. So our main objective is really to remove this cold zone in the lower part of the vessel. So you can see we have tried different design improvement, and so it seems like in the third and the fourth case, at least in this lower section, in the first two flux plan, we are seeing less cold temperature. However, in this third one, we're still seeing a lot of cold temperature, and in this entire vertical section, we are not expecting any cold temperature. Another thing we have done is really trying to improve the operation condition. So again, here the first one is the original design, and the second case is where we change the operation condition. So now you can see, even though we still see this maldistribution, one side is kind of colder than another side, but overall, we are totally removed this cold, this blue color This is really indicates some really low temperature, and we are able to totally remove that low temperature. And similarly, in the third case, we're trying to combine both the design and the operation condition together, and we saw a similar thing. So it's totally remove the cold temperature zone. So we think maybe we can, proceed with this kind of a design or operation improvement. So now this is the some data quantitative analysis on those different exploration. So in the Y here, I'm showing you the temperature, and the X indicate different kind of design or operation variations. The main goal, like I said, we're trying to make sure we don't have any temperature below the critical temperature. So in the original case, that's where we saw, and in a lot of design variations, we also kind of see that low temperature below critical. However, in the last two cases, you can see we are totally removed this low temperature, and even the minimum temperature is above the critical temperature. And this is a major, I guess, parameter we're trying to track to make sure we have the proper design and the chemical conversions. So with that, this is the summary. So we have tried to use the CPFD Barracuda with different size of fluidized bed simulation. And overall, I think, just by tuning some existing model, we are able to predicting the pressure drop, the bed density pretty well. But I do have some challenging, especially trying to match the pressure fluctuation. So sometimes it's really hard. It gave me like a 2-3 times difference from the experimental result. For the particle entrainment, yes, depends on the drag model you choose. You may match the experimental result. So I feel like difficult, especially for those high velocity range. So overall, like along this scale up process, we've been heavily using the CPFD as a tool to get into the design and operation. So we found it's quite useful to optimize the operation condition and building chemical engineering correlations. Yeah, I think that's it. Thank you.